Good afternoon, students. So welcome to Rapid Revision series. Today is the last lecture we are having. That is the topic we have the electronic devices, semiconductor electronics that we are going to cover today. So hope you are doing very well practice. And so this is the last week, and you might be revising some of the key terms, the formulas, and bio and chemistry also. You'll be revising some of the key concepts. Same goes for the physics also. Go and revise some of the concepts. Today we'll be discussing this. Today we have the last lecture, that is semiconductor and electronics. So what are the different topics that we are having without wasting your single precious time? So let's discuss what are we have the topics here. The theory of the semiconductor and p-n junction diodes. So in this chapter, chapter is divided into three parts. We can divide theory of the semiconductor and p-n junction diodes, where we're discussing the little bit theory about it, and application of the p-n junction diode. We have the Zener diode, we have the LED, we have the photodiode, we have the solar cell. Different types of diode we are using over here. Next, last part is logic gates. So if we see the weightage wise in this chapter, we can expect 3 questions. 2 to 3 questions we can expect. 1 questions we can expect from the theory of the semiconductor as well as diodes. 1 question we can expect from this application of the p-n junction diode, photodiode, LED and all. 1 question we can expect from this logic gate. So 2 questions if we are expecting. 1 question will mostly likely to come from the logic gate, and other question from this 2. Over the years it has been the trend that 1 question they are asking from the logic gates. Okay, so let's start this. So if we talk about the solids, so solids we can categorize in 3 parts. First is conductor, and second is semiconductor, and third is insulator. Conductors are the solids which conduct electricity and which will be having low value of resistivity, high value of conductivity. You can check this. Resistivity value is 10 to the power minus to 10 to the power minus 8, and conductivity value is 10 to the power 2 to 10 to the power 8. This is conductivity value. I would suggest you can memorize this, no problem with this resistivity and conductivity part. You can go through for it is for metals. Semiconductor insulators. Insulators are the materials which does not conduct the electricity, means they are having high value of resistivity and low value of conductivity. And we have that relation, that is resistivity is 1 by conductivity, or vice versa, conductivity is 1 by resistivity. So this both are reciprocal of each other. So insulators are the materials which does not conduct electricity. We can have plastic, we can have rubber, we can have wood. These are the insulators. Non-metals are insulators, metals are conductors. Next is semiconductors. The properties which lie between that of the metal and non-metal, that of the conductor and insulator. Those property, midway property, which is having by solids, that is what we define semiconductors. So semiconductors we are having silicon, we can say, we can have germanium. Those are the semiconductors we'll be having. So let's discuss the band theory on this. We have 2 types of band, valence band and conduction band, and forbidden bands over here. So what is this band theory? It talks about this. So if you talk about any elements, for example, if I say the element is sodium is there. So what is sodium? Electronic configuration 1s2, 2s2, 2p6 and 3s1. So here this is 1 valence electron is there for the sodium. If there are crystal of the sodium, there will be so many sodiums will be there. Each sodium is contributing 1 electron, that is valence electron. And this, how many sodiums will be there? Some infinite number of thousands of sodium atoms will be there. So what actually happens in general is that these electrons are bounded by the nucleus very much. So they are having little lower energy because this is bounded by nucleus, these electrons. There is one more electron, that is this valence electron. This is not that much bounded as compared to this previous electrons. So this electrons of this element, that is electrons of any other atom, all the atoms, they will combine and they will be forming one group. That group will be having certain definite level of the energy. Those level of the energy which is coming from the valence shell of the electrons from the different elements will be called as valence band. So this particular point, if we talk about this is having different number of electrons, 1 electron, 2 electron, 3 electron, 4 electron, like that will have different number of electrons will be there. And so in this there is one more scenario that 2 electrons will be having same energy. Again, These electrons will have different energy than these two. These two electrons will be having same energy but different energy than these two. As we are going above, the energy level increases. So energy level increases. So these are the electrons which is restructured in form of the energy levels. We call it as valence band electrons. And this group of energy levels is what we define valence band. Then what we have conduction band. The conduction band, some electrons will be very much free from the Coulombic force of attraction from the nucleus. So those are moving freely randomly. Those comes under this, they are having high energy, and those comes under the conduction band. Conduction band. So conduction band electrons are the electrons which is responsible for the conduction of electricity, and valence band electrons are the electrons which is bounded by its own atom, we can say. So this electrons is not responsible for conduction of electricity, but this electrons are responsible for conduction of electricity. So in case of the metal, this electron is more, this electron is almost there. Anyway, for any metal or non-metal or semiconductor, this will be almost, it will be filled. Valence band will almost fill, but conduction band will be partially filled for some kind of element, some kind of metals and non-metals will be checking over here. Then here we define energy band gap. So what is energy band gap? Energy required to move the electrons from the valence band to conduction band. Energy required to move the electron from this to this. This is what it define valence. This is what we define energy band gap. And this, let's say this one is EC, that is the lowest energy of the conduction band, and this one is EV, that is the highest energy of the valence band. That difference is what we define band energy gap. So this particular band energy gap will also determine whether the given solid is semiconductor, metal or insulator. So we're just discussing now this one, that is in case of the metals or conductors. So metals are conductors, that is the good conductor of electricity. If we have, we can see that conduction band which is responsible for conduction of electricity and valence band we are having, they are almost overlapping each other. Either they will overlap each other or they will be having band energy gap of less than 0.1 electronic volt. This kind of solids we call it as metals, okay, because the band energy gap value is less. On the other hand, if we talk about the insulator, the valence band and conduction band have very high difference, huge difference of energy. And what is the difference of the energy? The band energy gap is more than 3 electronic volt. We call it as, this will categorize under the insulators. This will be categorized under the insulators. Then there comes the semiconductor, for which the chapter is dedicated to. So if you talk about the semiconductor, so then we talk about the semiconductor for which the chapter is dedicated to. So semiconductor at 0 Kelvin, it behaves as insulator. So in this case, what actually happens is that all the electrons will be inside only valence band. So no electrons will be in conduction band. Right now at 0 Kelvin, the conductivity of the semiconductor is 0. Here, because it is not at all having any conduction band over here. But on the other hand, at room temperature, what actually happens that as the temperature increases from 0 Kelvin to room temperature, we have 298 Kelvin. So electrons will get the energy. So electrons will get the energy. As the electrons get the energy, some of the electrons from this valence band will jump into conduction band. Some of the electrons from valence band will jump into conduction band, leaving behind a vacant space, in which case valence band. So this is what we define hole, and this is what we define free electrons, which we'll be discussing just now. So this energy gap, whenever you have the band energy gap, that is the lowest conduction band electrons energy minus highest valence band conduction, highest valence band electrons energy is less than 3 electronic volt, then given material is semiconductor at with room temperature. What actually happens? Temperature increases. So temperature increases, more and more number of electrons will jump from this point to this point, this point to this point. So temperature increases, electrons will get thermal energy. Because of that, it will jump from the valence band to conduction band, valence band to conduction band, valence band to conduction band, and this will keep on happening. So this is also we define on temperature increases. What happens? Conductivity increases because more number of electrons is getting shifted to where? The more number of electrons getting shifted to conduction band electrons. So here in this case, it will be keep on. If it is temperature is rising, this will keep on jumping from here to here, here to here, like that. This is not in the case with the insulator and metal. Almost both are partially overlapping each other. So metals will be having conduction band and valence band almost overlapping each other. So let's move forward over here. That is, we define the intrinsic semiconductor. What is intrinsic semiconductor? Or we call it as pure semiconductor. The pure semiconductor will be defined as a semiconductor in which only single element is there. For example, silicon is there, entire crystal will be of silicon. If it is germanium, entire crystal will be of germanium. So what actually happens that here you can check that silicon is having 4 valence electrons. So this side it can take 4 electrons, it can get 4 electrons from this. So this is the pure silicon. Due to some reason, what actually happens that one electrons will get detached from its valence shell and creating one vacant space over here. This vacant space is what we define hole, and this is one free electrons. This is one free electrons. So here we define, this is what we define intrinsic charge carrier. The hole and as well as the electron, free electron, we call it as intrinsic charge carrier. In pure semiconductor, number of electrons Ne is equal to number of holes NH. NH means one electron will come out, one holes will be created, and that is equal to Ni. What is Ni? The Ni is the name given to intrinsic charge carrier, that is the either it is electron or the holes. Now this particular formula, that is Ne into NH equals to Ni square. This is always valid, and this is also what we define mass action law. This is always valid, and this Ne equals to NH, this is only for pure semiconductor. This will define for pure semiconductor. This one, that is I equals to IE plus IH. Current due to the free electrons which is roaming here and there inside the crystal, plus if we talk about this particular electron is watching that there is one hole, this will go and shift over here. There, this side holes will be created. Now this electron is watching that there is one hole, this will go and shift there. This side hole will be created. This electron is watching that there is one hole, this will go and shift there. This side hole will be created. Like that, electron is moving from one place to other. Looks like hole is also moving. So current will be because of both IE plus IH. So in general, at room temperature, this intrinsic semiconductor is having very low conductivity. That is of not much useful. So it, in case of germanium, or it can in case of silicon also, it is very less number of free electrons we have, so that we cannot use this as a form of in the form of electricity. For that, what we have, we are constructing what? Extrinsic semiconductor. And how we are getting this? So whenever there are two types of semiconductor, first is P type and second is N type. So P type semiconductor and N type semiconductor, that we are going to learn now. What is P type semiconductor? Whenever any semiconductor is doped with trivalent atom. So in this case, it will be doped with trivalent atom. So it will be doped with trivalent atom. So in this case, so what is trivalent atom? So BAlGa. So this one, yeah. So this one, if we talk about this BAlGa in, so this, if we talk about this silicon, and this is germanium, and here we have. Yeah. So here I was saying that if we talk about the silicon and germanium, when we're doping with this is what we define trivalent atom, and this is what we define pentavalent atom. So when we're doping with these elements, we'll be getting the p-type semiconductors. So what actually happens that if we talk about the boron, let's take the example of the boron. Silicon has how many? 4 electrons. So this side, so silicon has 4 electrons. So this one is boron. The boron will be having 3 electrons. So when the boron is having 3 electrons, actually it can take 3 electrons, it can give 3 electrons. But to get accommodated here, this requires 4 electrons. This requires 4 electrons. What actually happens that 1 electron will get detached from here, and that will be accepted by this boron over here, and this will become boron minus, okay, and this will be shifted over here, that is, this is boron minus. Now this boron will replace this silicon. So like that, what we are getting 1 free electron because of this boron. One more boron atom will come and 1 more free electrons will get. So what actually happening over the time is that one boron atom creates 1 hole. Okay, 1 boron atom creates 1 hole. 2 boron atom will create 2 holes. This is what is happening over the time. So what actually happens, we are doping the given semiconductor with the boron atoms, that is we define as impurity. So when it's doped with impurities, number of holes will keep on increasing. So 1 boron atom 1 hole, 2 boron atom will create 2 holes. Like that we have different number of boron atoms. We also call it as acceptor ions. So this is equals to number of the holes. So over the time, on doping with this trivalent atom, so number of holes will keep on increasing. Okay, number of holes will keep on increasing, and number of electrons will remain same, or relatively it will be decreasing. So here we define NH will become majority charge carrier in this, and this will be electrons, that is minority charge carrier. Because of this IH, obviously if hole is having more number of holes is there, so more number of electrons will be there. So in this case, IH will be very larger than IE. Conductivity, we have one relation. What is that conductivity? Sigma is given by N number of holes per unit volume into mu H, that is the mobility. Okay, mu H is the mobility, we can say the mobility, and this E. What is E? E is the charge of the hole. Okay, charge of the hole. So what are the key points that we should keep in mind? It is doped with trivalent atom. The number of holes is the majority charge carrier are the holes. The number of holes is very larger than number of electrons. Holes current is more than electrons current. Then we have conductivity is mostly dominated because of the holes we have. Number of acceptor ions equals to number of holes. Atom is electrically neutral. So this given crystal is electrically neutral. Crystal is neutral also. In this case, that we should keep in mind. These are the points that when we are doping this trivalent atom. So this is what we define extrinsic semiconductor, which case p-type. Next we have n-type, just opposite of this. Suppose if you are doping with this pentavalent impurities. So suppose silicon is doped with arsenic, or germanium is doped with phosphorus. What we are getting? We are getting the n-type semiconductor. So what actually happens that if you talk about the silicon is the element which takes the 4 electron and which gives the 4 electrons. But suppose if I'm doping this with the phosphorus is having 5 electrons, it can give the 5 electrons and it can take the 5 electrons, but that the rule is not satisfied over here. So what will happen? It will donate 1 electron, and this electron will become free electrons, and itself will become p plus, and this will go and attack over here, and this will be shifted over here. So 1 phosphorus atom is coming, 1 electron is released. 2 phosphorus atom will come, 2. So 1 phosphorus atom will give 1 electron. 2 phosphorus atom will give 2 electrons. As we are doping more and more with phosphorus atom, number of electrons will keep on increasing. So this will give rise to number of phosphorus atom is equals to number of electrons. Okay, this is also what we define acceptor donor ion. So number of donor ion is equivalent to number of electrons. Over the time, what will happen? More number of free electrons will be there in a given crystal, of this solid. So this side, number of holes will be very larger than number of electrons will be very larger than number of holes, and as the number of electrons is more, current due to electrons will be very larger than current due to holes, and conductivity is dominated because of this Ne into mu E. What is mu E? Again I told you, that is mobility of electron here. And one more thing that you should keep in mind, the mobility of electron is always more than the mobility of the holes. The electron is having more tendency to move than the holes. Okay, so mobility of electron is more than mobility of the holes. So next one is p-n junction diode. So we just discussed the p-type semiconductor and we just discussed the n-type semiconductor. This one is p-type, in which the majority charge carrier will be holes, and this one is the n-type, in which the majority charge carrier will be electrons. So p-n junction diode will be formed when we'll be getting the p-n junction diode. The p-n junction diode will be formed when p-n junction diode will be formed with this side we are having p-type semiconductor, and this side we are having n-type semiconductor. Okay, this side we have p-type and this side we have n-type. So p-n junction diode will be forming when p-type semiconductor and n-type semiconductor are brought closer to each other. So this side we are having more number of holes are there, and this side we are having more number of electrons are there, because this is n-type. So what actually happens, diffusion process happens until unless when there is an equilibrium is reached. So what actually happens, this side we have the holes and this side we have the electrons. The electrons will be shifting from here to here and holes will be shifting from here to here. The movement of holes from the p-type to n-type gives diffusion current, and this movement of electrons from this n-type to p-type also gives the diffusion current. This side will be getting, on the n side over the time will get the positive ions, fixed ions, and this side will be getting the negative fixed ions. So this creates a potential barrier. So holes are diffusing from the p-type to n-type because here concentration of holes is more and here the concentration of electron is more, it diffusing from n-type to p-type. So over the time this side will be getting negative charge and this side will be getting positive charge. This is what we are getting depletion region. And on the depletion region we can say that positive side is on n-type, so n-type will be having higher potential and p-type will be having lower potential, and that potential difference of n-type and p-type is what we define potential barrier. So this is what we are getting negative charge, this is what we are getting positive charge. Whatever the potential difference that is created between n-type and p-type, always n-type will be higher potential, p-type will be lower potential, and that is given by this particular relation where EB is the electric field between the depletion region and D is the width of the depletion region over here. And this electric field, because of this electric field, there is further diffusion is not possible. The electric field is created in such a manner that it stops the further diffusion, that is electric field exists in this particular region. So no more movement of these holes from here to here and electrons from here to here. And when the electron is moving from here to here and holes is moving from this p-type to n-type, this gives rise of diffusion current, and it is just opposite of that drip current in the direction of electric field. Because of the electric field, if electrons are moving, this is what we give rise to drip current. So we'll be discussing this one, right? So we have two types of this biasing. First is reverse biasing and second is forward biasing. So what is reverse biasing and what is forward biasing, that we'll be checking over here. So what is forward biasing? So if this one is p-type, this is, we define p-type, and this side we'll have a n-type. This side p-type and this side n-type. When the p-type is connected to higher potential and n-type is connected to lower potential, the given diode is said to be forward bias. And opposite of this, when the n-type is connected to higher potential and p-type is connected to lower potential, it is said to be reverse bias. So this will be like this over here. Now, so what are the key points that we should keep in mind here is that in this case, resistance of the ideal diode, if they are mentioned, it will be 0. Second point that you should keep in mind, that diffusion current increases in forward bias. Again, diffusion current increases in forward bias. And what about drip current? Drip current decreases. Drip current decreases. Okay. Next we have potential barrier. Potential barrier decreases. Depletion region decreases. Depletion region decreases. Potential barrier also decreases. Net electric field value also decreases. Also decreases. So in this case that we have during this, which case, that is forward bias condition, resistance of the ideal diode will be 0. And this diode acts as, if it is ideal, it acts as a switch. Switch is on. Like that, current will be flowing. It will behave as a connecting wire. Okay, it will behave as a connecting wire. So these are the pointers that we should keep in mind in when we talk about the PN junction in forward bias. Reverse bias, again, negative side is connected to higher potential and positive side is connected to lower potential. So this first particular point, that resistance of the ideal diode in this particular case is infinite. Resistance of ideal diode in particular case is infinite. Second is drip current increases, and drip current is current because of this because of the electric field that is exists in the potential barrier. Drip current increases. And what about diffusion current? Diffusion current is 0 in this case. Diffusion current is 0, almost reaches 0. And if we see the process, that is this side we have holes, that is p type, and this side here we have electrons, and this is potential barrier, and this is potential this is the depletion region over here, and this is positive, and let's say this has to be connected to negative because this one is p type and this one is n type. So p type should be connected to lower potential, n type should be connected to higher potential. So what is actually happening? Because of this, electric field also exists in this direction, and because already one electric field exists from the positive side to negative side. So this electric field and this electric field get merged, and it will give the rise of the net electric field more. So electric field, net electric field increases, E net increases. If E net increases, potential barrier also increases. Okay, the potential barrier also increases. Potential barrier increases. Width of the depletion region also increases. The width of the depletion region also increases. These are the points that we should keep in mind. So last point, diode act as a open circuit. So like switch is off, the switch is not closed, we can say switch is open. So diode act as open circuit. Okay, so does not current is what current we have? Drip current. This is order of microampere. That is almost negligible for our daily life current that we have. This is the order of microampere. So this drip current is very less current. We can say that diode is acting as open circuit. It does not flow, does not conduct a current, we can say in this case. Okay, so these are the points that we should keep in mind in reverse biasing. Next we have this IV characteristics, and if we plot the graph of this I versus V. So what is I versus V? So this current versus voltage graph. So this region is forward bias region and this region is reverse bias region. What actually happens that initially when the voltage increases, current value is 0. Up to certain value, the current value is 0. This particular value is what we define potential barrier. So for example, potential barrier for this silicon we have, potential barrier for the silicon we have, that is 0.7 volt, and potential barrier for germanium that we have 0.3 volt. So at least we need the battery of 0.7 volt so that this silicon will conduct the electricity in this. If you are giving germanium, minimum voltage is required is 0.3 volt. So after that, this potential barrier current will start increasing like this. In which case, forward bias. On the other side, reverse bias, that is, it start from the negative side. If we see that current value is in the order of microampere. Okay, this order of milliampere or ampere, but this is order of microampere. The current value is 0. At this particular voltage, we call it as breakdown voltage. What actually happens that this current starts increasing abruptly in the reverse bias. This is due to breaking of the covalent bond of the silicon atoms of any semiconductor elements. So this is due to the breaking of the bonds, and that happens at one particular voltage. We call it as breakdown voltage, and this is also we call it as, this particular graph is for Zener breakdown. So Zener breakdown, it is the process in which the current value will keep on increasing but the voltage will remain same. So Zener breakdown, right? So let's see some of the questions that we have. As the temperature increases, the electrical resistance increases. Temperature increases. temperature increases, resistance of the metal or conductor increases, but for the semiconductor, because as the electron is jumping from valence band to conduction band, more number of electrons are there. So for semiconductor, temperature increases, resistance decreases. So resistance of the semiconductor decreases. That's it. So increases for conductor but decreases for semiconductor. For a p-type semiconductor, which of the following statement is true? Holes are the majority charge carriers and trivalent atoms are dopants. Holes are the majority charge carriers and pentavalent atoms are dopant. So this one is correct. Holes are majority charge carriers and trivalent atoms are dopants. Okay. In an n-type semiconductor, which of the following statements are true? Holes are the minority charge carriers. Yes. N-type semiconductor, electrons are the majority charge carrier and pentavalent atoms are dopants. This also statement one is correct. Holes are the majority charge carrier. No. Electrons are majority charge carrier and trivalent, no, pentavalent, right? Electrons are the magnetic carriers and pentavalent atoms are dopants. No, it is majority, right? The electron concentration in n-type is the same as the hole concentration in p-type. So Ne is equals to Nh. Okay, fine. An external electric field is applied across each of them. Compare the currents in them. So I told you. So current is because of Ne multiplied by mu multiplied by E, right? What is mu? Mobility. Now I told you both are having same charge, number is also same. So mu will depends. I is proportional to mu. Whose mu is more? The mu of electron is more than mu of the holes. So current of the holes, electrons will be more than current in the holes, right? So current in n-type will be greater than current in p-type. Because in n-type, current is mostly because of the electrons and electrons are having more mobility, right? Pure Si at 500 Kelvin. So this one is having number of electrons and Ne concentration of 1.5 into 10 ki power. So what is this Ni? Ni value is 1.5 into 10 ki power 16 by per meter cube. By doping with increases, Nh increases to how much? This one. So now, what is Nh? Nh is 4.5 into 10 ki power 22. So we are doping with trivalent atom. The number of holes is increasing over here. So what they're asking? The number of electrons they're asking. So again, it is a p-type semiconductor because we are doping with which one? Indium. What is indium? Trivalent impurity. We are doping in trivalent impurity. So this n-type and this n-type is getting cancelled. Your options are either option 1 or option 3. So here we have to check which one is Ne. We have to check which is Ne. So what is formula? Ne multiplied by Nh is equals to Ni square. So what is Ne? What is Ne we have? That is what we have to find. So Ne multiplied by Nh. What is Nh? 4.5 into 10 ki power 22 is equals to Ni square. What is Ni square we have? This one 1.5 into 10 ki power 16 whole square. So this side, if we solve this, so this will be Ne into 4.5 into 10 ki power 22, 1.5 is square. This is we are getting 2.25 into 10 ki power 32. So 1 and this one is 0.5. Okay, this will be 0.5 into 10 ki power 10. So 5 into 10 ki power 9. Answer is option A. Okay, this is the correct answer. We are getting this. This particular question we can use for any type of semiconductor, but this one Ne should be equals to Nh should be equals to Ni. We'll be using only for pure semiconductor, right? Next we have the question is coming from the forward bias and reverse bias. So forward bias and reverse bias, let's check it which one is forward bias and which one is reverse bias. This is higher potential and this particular point will be lower potential. This is lower potential, this side higher potential, this side higher potential, this side lower potential. So we can check this. This will be lower potential. This is forward bias because P type is connected to higher potential, N type is connected to lower potential. This is reverse bias because P type is connected to lower potential and this is connected to higher potential. So this one is reverse bias. So I told you if it is forward bias, just cut it, just remove the diode and paste it like line. And if in this case we have to open this, so this circuit will be reduced to here the diode is there and here diode is not there. It looks like connecting wire. So it will be look like because this one is forward bias and that one is reverse bias. So that's it. That's it. So we'll be solving this. Okay. So we'll be solving like this. So here, what is current value? This one is 20. This one is 30. And here we can write what is current. What is asking current now? So what is current? This one is 5 volt divided by 20 plus 30. 5 divided by 50. Answer is option B. Right. So moving next, the diode used in the circuit shown in the figure has a constant voltage source of 0.5 volt at all current and at all current. So there is constant voltage source of how much? This one is 0.5 volt. This is what we can define. This is the potential barrier of the diode. Means it will take a 0.5 volt its potential barrier. Remaining how much we have? 22 volt in this 0.5 volt. So remaining potential difference how much we have? That is 1.5 volt that we are having. That is across the resistance we have. What they're asking? Maximum power rating of 200 milliwatt. So this is the maximum power rating. P max is equals to 200 milliwatt. And I told you what is. I will tell you what is this. 200 milliwatt. This maximum power rating means beyond this power rating, this diode will get damaged. So maximum power will also give the maximum current. What is the maximum current from? We can calculate. The power is given by V into I. Whenever the resistance is not given, we will be using this particular formula. 200 into 10 to the power minus 3 watt. So this, what is voltage? 0.5 into current I is equals to 200 into 10 to the power minus 3 watt. So this will go that side. So we are getting, so I is equals to how much? This will be 400 into 10 to the power minus 3. This is ampere. Okay. Next, what they are asking? What should be the value of the resistance R connected in series? Now we got the potential difference across the R. We got the current from there. We have that relation V is equals to I into R. Okay, V is equals to I into R. So this I value that we are getting from here is 0.4 ampere. So what is V? V is 1.5 volt is equals to I multiplied by R. So this is 0.5 multiplied by R. So what is R? 1.5 divided by 0.4. So this 15 by 4 is equals to R. So what is R value? 3.75 ohm that we are getting from this calculation. We calculated the maximum current that can be flowing through that diode, and whatever the current that is flowing through this diode, the same current will be flowing through this resistance elsewhere. We calculate what is potential drop across this, and from here we got this R value, that is 3.75. Right. The general diode is connected in reverse bias when used as voltage regulator. Yes, voltage regulator, general diode is we use as voltage regulator that across whatever the electrical appliance that has to be supplied at constant voltage, that is always connected in parallel with the general diode, and it is operated in reverse bias. The potential barrier of the PN junction that lies between 0.1 to this statement is wrong, because the germanium is having the potential barrier of 0.3 and not less than 0.3. We don't have any semiconductor which lies whose PN junction potential barrier is less than 0.3. So this statement is wrong. Statement 1 is correct and B is wrong. Answer is option D. The photovoltaic devices can convert optical radiation into electricity. Yes, photovoltaic devices which depends on the depends on the light. So photovoltaic devices, for example, photodiode we have. The photodiode, that this one will be discussing this one. Yeah. So we have three types of optoelectronic devices. First is LED. What is LED? This is operated under forward bias condition. Forward bias condition, and this one is highly doped semiconductor, highly doped PN junction diode. Okay, highly doped PN junction diode. This is highly doped PN junction diode operated in the forward bias condition. What actually happens is that what actually happens during this process, when it is connected in forward bias condition, more and more holes are transferred from P type to N type, P type to N type, and from electrons transferred from N type to P type. During this, there is a combination of electron as well as holes takes place. So this is silicon atom. If we talk about this will be silicon atoms, and these are the electrons will be there, and somewhere it will be holes, and this one electron. This electron will get combined with this particular holes. This will give release in the form of energy, release form in the form of light. This light is what we define light which is coming from the LED. So depending on the types of the diode, we'll be having different colors of the light. Now, if we talk about this graph, the graph is not this one. The graph will be given by this forward bias characteristics because it is operated under forward bias, and as we are moving across this wavelength value decreases. Okay, as we are moving left to right, wavelength value decreases. So wavelength of the color of the light which we are getting from the LED will keep on decrease. This is the circuit symbol where the light is coming out from this. If you talk about the photodiode, what is photodiode? The photodiode is based on the principle that is electron hole generation. So whenever the light falls on the silicon or any semiconductor we have, what actually happens that the silicon atoms, electrons will be there. This electron, the photons will be striking this atoms, and this electron will come out. The photons will be striking this electron, and this electron will come out. As the light is striking the given element crystal, the outermost shell electrons is coming out and is becoming free electrons. This is give rise to electron hole pair generation because electron is coming out from its valence shell, creating a hole there. Electron is coming out from here, creating a hole there. So this is governed by this which process? Reverse bias process. Okay, because in reverse bias the current value will be less, and we want very less amount of current because its purpose is to detect the light. If you are able to detect the light, very small amount of light, our job is efficiently done here in case of the photodiode. So reverse bias, and this is low dope semiconductor, so that electrons and holes is generation takes place, low dope semiconductor. And if you talk about the graph will be for reverse bias condition, and as we go down this intensity increases. This thing that you should keep in mind, intensity increases. And here we also one particular term that is Eg. What is Eg? Hc by lambda. Eg is the band energy gap of the diodes, and this Hc by lambda, the light that can be detected by this diode, Hc by lambda. Lambda is the wavelength of the light we have. Next we have solar cell. Solar cell is just this is operated no biasing condition, forward bias is not required, reverse bias is not required. So it will be just a diode connected with a capacitor, we can say. A diode connected with the capacitor. So what actually happens? A light will fall on this, whatever the extra holes or electrons that will be stored over here, and this also will be stored over here. As the light, more and more light are falling, more number of electrons and holes are generated, and electrons, this will become negative charge and this will become positive charge. It is connected negatively charged particle. This will be solar cell design, we can say. And here we have two terms. This particular graph, this is open circuit voltage. What is open circuit voltage? When the circuit is open, when the capacitor behaves, after some time when the capacitor is fully charged, this will give open circuit voltage. What is short circuit voltage? Initially, whatever the short circuit current, initially when the capacitor is not at all charged. So not at all charged, when the charging takes place, once it gets fully charged, no further accumulation of the charges inside the capacitor once it is fully charged, and this will give rise to open circuit voltage. The graph will be like this. So this graph that you have to remember for this solar cell. Now coming back to this particular question that we were solving here. Photoelectric devices can convert optical radiation into electricity. Yes, whatever the optical signal that is falling, it is converted into electricity by means of electron hole pair generation in case of the photodiode. Generator is designed to operate under reverse bias in breakdown region. Yes, this statement 1 is also correct, statement 2 is also correct. Both statement 1 and 2 are correct. So this one numerical question that we can see from this Zener diode. So what is Zener diode? Zener diode is the diode which supplies the constant voltage across this particular point. So this point and this point, this will be supplying the constant voltage. So this side also it should be supply the constant voltage, and whatever the constant voltage we want for this, for example, if you want the constant voltage for the refrigerator, we will be connecting that refrigerator in parallel with this Zener diode. So this Zener diode, the circuit symbol is like this, okay, and whatever the things that is connected in parallel with this will get the same potential difference of 15 volt. Now here we have this particular symbol gives the source voltage, and this is what we define load resistance. Across the load resistance, the value of the voltage will be same. So here current is, let's say current is flowing here I, the I part will be distributed where this will go, that is IL across this side, and this will go, that is IZ. I will be writing the current through diode. What they're asking? Current through diode they're asking. So let's say this one is 0 volt and this one is 20 volt. This will also be 0 volt This will also be 0 volt because they are connected by single line. Now the points will change, the value will change. So this one is 15 volt and this also 15 volt. So if I talk about the current, if I apply the Kirchhoff's KCL law, I is incoming, this side IZ is going, plus this side IL is going. Okay, so what is I? We want to calculate potential difference across this. So this side 20 minus 15 divided by resistance. 20 minus 15 divided by resistance 250 is equals to what is IZ? That is what we have to calculate. So IZ plus IL. What is IL across this? 15 minus 0 divided by resistance. What is the resistance here? 1 kilo ohm, that is 1000. So after solving this, so 20 minus 15, 4 by 2, 5 by 250 multiplied by 4. So this will be getting 16 by 1000 minus 15 by 1000. Okay, is equals to IZ value. So what is IZ that we are having? Just a second. This is 5 now. This is 20 by 1000. This will be 20 by 1000. So 20 by 1000 minus 15 by 1000. We are getting this 20 milliampere minus 15 milliampere. We are getting this 5 milliampere. That is the current which is flowing through this Zener diode. Answer is 5 milliampere. I hope this is clear to everyone. So this is how we'll calculating the question, numerical question from the diode, Zener diode. Then we have half wave rectifier and full wave rectifier. What is half wave rectifier? Whenever you are coming across this kind of setup in which we'll be having, this side will be having primary transformer. This is primary circuit. This is primary coilover transformer and this one is secondary coilover transformer. What actually happens that in case of the half wave rectifier, we can see that this is the input circuit that is fed at point A. This is positive, negative, positive, negative. This is what we have alternating current or alternating voltage. But on the output circuit that we are calculating at this point. So here we can only check that only the positive cycle is there. The negative cycle is disappeared in that. So this gives the direction of the current in one direction only. This gives correct current in one direction only, not in other two directions. This is input for the direction is positive. This is half wave rectifier. We can check whether the simple diode is one single diode is connected. So this one is positive, this one is negative. Let's say this one is positive, this one is negative. Initially for first half cycle this will be forward bias, for the and after next half cycle this will be reverse bias. So no current will be flowing in reverse the next half cycle. So this gives rise of this, and here we can write frequency of AC or frequency of ripple in this case is equal to frequency of input circuit. Okay, so this is one time period, this is also one time period, this is two time period, this is also two time period. Time period for this one, this is same. So frequency of ripple in half wave rectifier only, just both are equal. Input AC frequency and this half wave rectifier frequency, both will be equal. Here center tap transformer is used to determine, used to find out the full wave rectifier. What is full wave rectifier? In half wave rectifier we say that only positive side we are getting. So this will be input circuit. And what about output? Output will be half wave as well as full wave. So this first part, this will be second part, third part, fourth part, fifth part. That all the waves forms will be taken care. So this will be input and this will be output. So in the output circuit, what we have, this is also there, this is negative side is also there, this positive side is also there, and again negative side is also there. So this is there is no disappearance of the ripple in this case. So this is the full wave rectifier where the complete AC waveform will get filtered over here. Now, so this case we will be having two kinds of diode, the diode D1, diode D2. For the first half cycle, this one is forward bias and this one is reverse bias. For the next half cycle, this will be reverse bias and this will be forward bias. But overall, the output circuit current value will be same, that is from X to Y. Okay. So, and if they're asking, so this is one time period of output and this is one time period of input. So I can write time period of output is half of the time period of input. So frequency will be doubled. The frequency of the output in case of the full rectifier equals to 2 times the frequency of the input. So these are the things that we should keep in mind. In half wave rectification, if the input frequency is 60 Hz, then output frequency would be given by input frequency 60 Hz, output frequency. I told you, half wave rectification, whatever the frequency of AC in input will be equal to frequency of output, in which case half wave rectifier, that is how much? 60 Hz, right? So consider the following statements: A and B, identify the correct answer. For a solar cell, the IV characteristic lies in 4th quadrant of the region. For the solar cell, IV characteristic lies in the 4th quadrant of region. So this will be solar cell, right? This will be for LED. You can note down this on a single page. This will be for LED, and this will be for solar cell. We have this one is for solar cell, and we also discussed 2 more diodes. First one is photodiode. We discussed for the LED photodiode. The photodiode will be this one, reverse biasing. We also discussed the Zener diode. Zener diode will be for this one. This is the Zener diode voltage. This will be Zener diode, and this will be, we can say, this one is photodiode. Okay. In a reverse bias condition, PN junction diode, the current measured in microampere is due to majority charge carriers. In a reverse bias condition, PN junction, the current measured in microampere. In reverse bias condition, current is mainly because of drip current, and drip current is mainly because of the minority charge carrier. So option A, that is statement A, it lies in 4th quadrant. Yes, the solar cell graph lies in 4th quadrant. Statement 1 is correct, but this one is incorrect. A is correct, but B is incorrect. The IV characteristics for both are given by. So again, whenever this voltage is given and this side current is given, so this graph is for solar cell. This particular point will be called as open circuit voltage. Okay, this particular point we call it open circuit voltage, and this particular point will be called as closed circuit current. Closed circuit current. So this is for solar cell. So that is for the semiconductor. We have next, we have this one more thing, that is, but not the least thing, that is the logic gates. So first is NOT gate, AND gate, OR gate. So we have this particular symbol, and there are certain Boolean, just a second, just quickly I will go through the Boolean algebra. So I hope all of you will be knowing this Boolean algebra. So in that we'll be having this side, if we addition, if we do multiplication, and if I do inverse, so this side will be having inverse. So if I do addition, means 0 plus 0, that will be 0. Okay, 0 plus 1, that will be 1. 1 plus 0, that will be 1. 1 plus 1, again that will be 1. If any of the input is 1, then output will be 1. So these are the, what we are adding, we call it as input. Okay, this 0 plus 1 is 1, and what we are getting, that is the output we are getting. So next, if we talk about the multiplication, 0.0 is 0, 0.1 is 0, 1.0 is 0, 1.1 is 1. If any of the input is 0, whatever we are on the left hand side, that is input. 2 inputs we have, 0.0, we both are 0. If any one of them are 0, the final output will be 0. Like that we have 0 inverse is 1, and 1 inverse is 0. 0 double inverse is again 1 inverse, that is 0, and 1 double inverse is again 1 inverse. 0 inverse is again, that is 1. Second, certain in terms of the A and B, will be writing this. So if we talk about this A plus 1, anything plus 1, when we are writing this 0, either put A equals to 0 or A equals to 1. So this 0 plus 1, 1, or 1 plus 1, 1. So A plus 1 is 1. Like that we have A dot 1, A dot 1. Like that here we have A dot 0. So this, I'll be writing this. If A value is 0, 0.0 is 0. If A value is 1, 0.0 is 0. Okay, so 0 plus A, 0 plus A. If it is A is 0, 0 plus 0, 0. If it is A is 1, 1 plus 0, 1. So 0 plus A is A. Here we have A dot 1. A dot 1 is also A. A plus A we don't write 2a, we write only a. Okay, we don't write 2a, we write only a. Here a dot a, this will be a only. Now a plus a bar, this is equals to 1. A dot a bar, this will be equals to 0. That's it. We'll be checking different cases over here. Now this a double bar is a and b double bar is equals to b. Then we have De Morgan's law, that also we'll discuss this. De Morgan's law. So in De Morgan's law, what we have, a dot b whole bar is given by a bar plus b bar, and this is not equals to a bar dot b bar. Remember this. Okay. Second, a plus b whole bar, that is given by a bar dot b bar, a bar dot b bar, and this is not equals to a bar plus b bar. So this is what two laws will be having. We'll be solving questions from here also. So for different types of the operations we have addition, for that there is one dedicated gate, that is what you define OR. For multiplication dedicated gate, that is what you define AND. And for inverse dedicated gate, that is what you define NOT. Then if we combine this OR and NOT, we'll be getting this NOR gate. If we combine this AND and NOT, we'll be getting this NAND gate. So we'll be discussing that now. So first one is NOT gate. This is the circuit symbol we have. Whatever the inputs, you have to get the output as opposite of that. So 0 inverse is 1. 1 inverse is 0. This is what? NOT gate. What is circuit? If this one is A, what is X? I'll be writing X will be A bar. Okay, this is the circuit. This is the what we can algebraic operation. This will be a Boolean operation for this NOT gate. Next we have this one AND gate. What is AND gate? This one is input is A or input is B. What is output? X. This particular gate is AND gate. So X will be writing here A dot B. Again 0.00, 0.1 0, 1.0 0, 1.1 1. Right. Next OR gate. So OR gate means X equals to A plus B. So either of the input is 1, output will be 1. 0.0, both the input is 0, output will be 0. One of the input is 1, output is 1. 0 plus 1, 1. 1 plus 0, 1. 1, 1, 1 plus 1, 1. This is what we define OR gate. You can note down this circuit symbol also. This one is NAND gate. What is NAND gate? NOT of AND. So this side, NOT gate, NOT plus AND. Okay, or I can say it is reverse of that. That is AND plus NOT. AND plus NOT. So AND gate plus NOT. Okay, this is AND plus NOT. So first we can get it AND gate and just do the opposite of this. What is AND gate? Final output we are getting 0 0 0 1, right? So this will be 1 1 1 0. This is also we 1 1 1 0. So we have to do first AND. So let's check this. This will be A and this will be B. So this will be A B. This is AND, and we have to do the opposite. That is, we have to do inverse. A dot B ka whole bar. And this one is NOR. What is NOR? The NOR, if you break it, this will be NOT plus OR. Okay, this will NOT plus OR. NOT plus OR. So first OR will be there. Because of this OR, this will be A plus B. Because of the NOT, A plus B whole bar. So this is Y. And whatever the OR circuit, this we are getting, that is 0 1 1 1. So opposite of 0, this will be 1 and this will be 0 0 0 over here. That is 0 0 0. And two more that we define: single input NAND gate, single input NAND gate, and NOR gate. So this we have, suppose if this one is NAND gate, just connect this by a single line. Both the inputs are same. Now this will be A and this will be A or A. This is A dot A ka whole bar. That is nothing but A bar only. So this is the input and this is the output, equivalent to this is what? NOT gate. Okay. Similar for this we have, if we have this NOR gate, this one is single input. This side A we have and this side also we have A. So this will be A plus A ka whole bar. A plus A ka whole bar. So A plus A only, A bar. So this is also acting as a NOR single input NOR gate, and single input NAND gate will act as a NOT gate. Okay, will act as a NOT gate. Right. So let's see some of the questions based on this. So this is what gate. Again, I told you this one is a single input NAND gate. So this will act as a NOT gate. This will also act as a NOT gate. So this here input is A, and in this side input will be, output will be A bar. Here input is B, and this side this will be B bar. This will be A bar, and this will be B bar. And this side we have A bar. This is A, this is A bar, this is B, and this will be B bar. And this particular things that we are writing, this is again NAND gate. So if I write this, that is nothing but A bar dot B bar ka whole bar, right? A bar dot B bar ka whole bar. And how we can get this A bar dot B bar ka whole bar? So if I do this, what we call De Morgan's law, what is A dot B ka whole bar? That is A bar plus B bar. So A bar ka bar plus B bar ka bar, right? So this A bar and B bar is one input, A bar ka bar plus B bar ka bar. What is this? We are getting A plus B. So what is A plus B? This particular symbol is for OR gate, that is A plus B, right? Again, so let's this one is A. Again, this is single input NAND gate. It will act as a NOT gate, I told you. So this will be A bar. This is single input NOR gate. Again, this will act as a NOT gate. So this one is B, and this side will be having B bar, right? This will be B bar. So this will be A bar, and this will be B bar. Okay, this will be A bar, and this will be B bar. So this side, again, this is what NOR gate. So what is NOR gate? A bar plus B bar ka whole bar. Okay, A bar, A plus B ka whole bar is a NOR gate. But here the input for this NOT gate is A bar plus B bar. A bar plus B bar ka whole bar. That we are getting how much? If I De Morgan's law, A plus B whole bar. A plus B whole bar. That is A bar dot B bar. So here A bar ka bar dot B bar ka bar. What we are getting this? A dot B. A dot B is for which gate we have? NAND gate. Sorry. A bar, A dot B for which gate we have? AND gate. Okay. So circuits, this one, A bar, A bar NOT gate, A dot B AND gate, A plus B OR gate, NAND, A dot B ka whole bar, NOR, A plus B whole bar is NOR gate, right? So this particular question, the question is saying that here we have plus 6 volt, and here we have resistance, and here we have LED. Okay, here we have LED. Now when the LED glows, we write it as 1. When the LED does not glow, we write it as 0. If the circuit is open, we write it as 0. If the circuit is closed, if the key is closed, we write it as 1. So let's say this is the key 1 and this is key 2. So let's say I am writing this key 1, key 2, and let's talk about the bulb. If it is glow, you write it as 1. If not glow, if does not glow, we write it as 0. Okay, if it is closed, open is 0 and closed is 1. Open 0, closed 1, right? So open 0, closed 1. Open is 0, closed 1. Okay, suppose let's discuss this particular question over here. Now current is coming here, the voltage is 6 volt, current is coming from here, current is coming from here, current is coming from here, current is coming from here. But to glow the bulb, current has to go to lower potential, then only bulb will glow. So if both are open, the bulb will not glow because the current is not reaching its lower potential value. Current is not completing its circuit, we can say. So suppose both are open, this one is 0, this one is also 0, bulb does not glow, this will be 0, right? If any one of them is closed, if this one is closed, what will happen? Current will come like this, go like this, go like this. This is 0 potential. In this case, bulb will glow. So this one is 1, this one is 2, this one is open, this one is closed, then also bulb glows. Reverse case, this one is open and this one is closed. This one is open and this one is closed. Then what will happen? Then also current will be coming like this and going like this. So this is 1, 0, 1. If both are closed also, then also current will go like this. So this is 1, 1, 1. So which circuit we are getting here? Either of the input is 1, output is 1. Which circuit we are getting here? OR gate. So this particular circuit symbol is equivalent to OR gate. Okay. Okay, so last question of this we have. So this one is A. Okay, this input is also A. Here it is A, but as it is jumping this NOT gate, this side input will be A bar, right? And whatever this one, this is B, just B. And this also just B we have at this particular point. For input for this particular NAND gate, we have NAND gate, this one is NAND gate. Okay, this one is NAND gate, and this is also NAND gate. So input for this particular gate is NAND gate. So this NAND gate we have A and B. So this will be what? A dot B whole bar. Okay, and what is input for this is A bar, and this side we are having B. So this A bar and B will act as input for this NAND gate. So this will be having A bar dot B whole bar, and this is the final one. And what is final one? This one is which gate? AND gate we have. And what is AND gate? Now this is the input for this, and this is also input for this. So this will become A dot B whole bar whole dot A bar dot B bar ka whole bar, right? So this is the output that we are having, and let's calculate this one, then our problem will be solved. So what is Y? What is C? We can write. So C is the output, the final output, A dot B whole bar. So this will be A bar plus B bar. I hope this is clear, because this is A dot B whole bar, A bar plus B bar. Next we have this one, A bar dot B whole bar. So this will be A bar ka bar plus B bar. Okay, so this C we can write here further, A bar plus B bar, and this one is A plus B bar. So open this. So C is equals to A into A bar plus A into B bar plus B bar dot B bar plus B bar dot A bar. So A into A bar, anything, if A is 0, this is 1, 0.1, 0. If A is 1, this is 0, 1.0, 0. So this will be 0 plus A B bar. We have to calculate that. So let's, if I take B bar dot B bar, that will be B only, B bar only, B bar plus B bar A bar, right? So if I take this 0 plus something, if I take this B bar common, so this we are getting A plus 1 plus A bar. A plus A bar 0, so this getting B bar, and what is this? 1 plus 0. The final output should be getting B bar. So we have to check B bar, that's it. C is equals to B bar. So let's check this one. 0 1 1 0 0 1 1 0. Answer is option A anyway. Let's check here. 0, this is 0. No, this one is correct. C should be B bar. 0 1 1 0 0 0. No, this is wrong. Right, this one. 0 0 1 1 0 1 and 1 0. So this will also be wrong over here. Okay, so that's it for this today's topics. So what next? So wishing you all the very best for your NEET examinations that is coming on the next 4th of May. Wishing you all the great success here. All the very best, and hope you will do your best. Keep revise in these 5 days. Keep revising the formulas, biology part, chemistry part also, some key concept, some theoretical concept. You go and revise and do your best, and we all hope for the best in coming NEET 2025.